So I'm having, oh, there we are, woohoo. Hello. So it's really interesting to follow Jens's really deep discussion of indexicality against a project that is reaching for the index, that is reaching for the real, in order to think about how we can make environmental health more manifest. So I'm going to be discussing a couple of the problems with capturing late industrial environmental health problems like endocrine disruptors, in part because many of them are invisible, so we're probably all being exposed to flame retardants, for instance, by sitting in these chairs, and yet our health science will deal with the outcome of that in our future children and we really don't have a great way of capturing the collective nature of these exposures or in dealing with this invisibility and latency of environmental hazards. So I'm going to be discussing today a couple of projects where I'm trying to rethink the process of environmental science research by changing the kind of tools we use for environmental work and the kind of process behind our science. That actually borrows from the history of science, where in the formation of scientific societies, really witnessing the index was key to making a scientific matter of fact. So the initial scientific societies would welcome gentlemen because they were able to credibly watch things, and they would provide evidence of what they saw. And science was performed. It had a very performative aspect in the 17th century, and I couldn't help but include this performance of the fact that human bodies can electricity that involved actually electrifying a child and putting metal objects around the kid so that metal would fly towards the child. So a real interesting index, and one that you certainly couldn't get through an IRB now, but going back to the idea that historically science really was organized as a spectacle. And we have since made science much more sterilized and isolated, literally, in the way we perform it. So this is the way an air sample is taken in a home now, in a standard EPA procedure. It's called a Summa canister. You basically open it, it grabs air from the home, and then it will be shipped to a lab where an expert, and you know they're an expert because of their white coat, will analyze it and provide you with data as to what's in that sample that's graphical in nature and really not embodied in the sense of what it's like to breathe the air in that living room. So the environmental sciences in particular have organized themselves around a very extractive model of work where we take samples from the environment, we move them to the lab, to a space that most people have very limited access to, and we produce results in a way that are very unfamiliar to the body that's actually experiencing those exposures. This is a particular problem, I argue, in studying large-scale industrial environmental health threats like the one emerging from the unfolding of unconventional energy extraction across the US. So 15 million Americans now live within 1 mile of an oil or gas well that's been drilled since 2000, and it's leading to shapes like this one, where you can see the blue residents surrounded literally by oil and gas wells. But there is very little monitoring of those individual wells as sources of water, air pollution, and ground pollution. And so we've been picking up one way to look at one actually very well-known and understood hazard. That's hydrogen sulfide, as Lourdes described earlier. H2S is a neurotoxic gas, and about 15 to 20%, 25% of the wells in the US could be contaminated with this gas. And yet there is no federal reporting of emissions from those sites of oil and gas extraction. And this is very because it's a leading cause of workplace injury in the US. It's not as if we don't know that hydrogen sulfide is a risk. So the current thinking is that you shouldn't be exposed to more than 1 part per million for an 8-hour workday of H2S. And you know, this whole in regulation isn't an accident. There's been over 20 years of industrial lobbying from industries that produce H2S to try and make sure that they don't have to disclose how much H2S they're emitting to things like the toxics release inventory. And so this means that all of those oil and gas wells around the country currently only need to have plans in to prevent and respond to accidental releases to hydrogen sulfide, where H2S is framed as something that might be accidentally produced, not chronically produced. And it's leading to very strange situations where, if you remember back to that house that's literally surrounded by red dots, if somebody is working in one of those red dots, and it to be a high hydrogen sulfide zone, they'll be trained in what hydrogen sulfide is. They may be working with supplied air in case there's high enough levels that would knock them down, knock them out, and possibly kill them. And they'd be carrying an alert badge to let them know if what have been determined as acute thresholds for hazard have been exceeded. Whereas you might have residents who live right next to those wells, who perhaps work in fields or around them every day, have no training on those risks. There's no monitoring in place. And the monitors that we have designed, you know, the way we frame something legally does shape the kinds of tools we use to know them, produced things like the Jerome Meter, which is the industry standard way of monitoring H2S. It costs about $15,000. It's really designed for looking at acute levels of H2S to let you know when thresholds of acute risk are exceeded. And it's trained to think about individual work exposures. And that's very different from the community exposure experience. So what I'm going to describe now is how our photographic paper method is an attempt to capture the community exposure experience better than a Jerome Meter can, because this is the kind of warning a community member might expect to find. Corroding sign, and it's corroding perhaps because of hydrogen sulfide, saying that H2S may be present. That doesn't even spell out the name of the gas. And yet, one of the ranches where we worked, this is just a third of a mile from their home, and they work and they have their livestock in the fields around those wells all the time, grazing. And as the rancher said, she expresses symptoms of H2S exposure, burning to her nose, feeling that her chest hurts, and the feeling of mental slowdown. And her livestock have also shown problems. So they raise meat goats, and they pastured in the field just below the oil wells on their property, had a very high rate of miscarriage that they think is associated with exposure to H2S. And there are many well-known problems now with chronic H2S exposure. And you can be exposed to H2S from natural sources too. And so, for instance, a study in Hawaii found an 11-fold increase in central nervous system disorders in communities exposed to H2S. So things from respiratory distress to fatigue and dizziness to central nervous system dysfunction. But so from a community perspective, the exposure experience is very different, right? You're looking at low-dose exposures, where you're concerned not just about the working individual, but about vulnerable populations like children and the elderly. You're concerned about the health of the environment as a whole, and H2S is ecotoxic to aquatic life at very low levels. And yet, you know, against that, we have structured an agency in attention to this issue. So the social exposure experience is very different. There are no mandatory regulations to look at levels of H2S, so people aren't trained about the risks. There's an absence of data, and this contributes to communities really feeling beaten down, like there's nothing they can do. They can either abandon their property, they might get in a protracted lawsuit, but there's really nothing they can do to shift this system. And I doubt this will shift the system entirely either, but it's an attempt to think about how can we create a more performative kind of data for these communities that, rather than showing exposures on an individual level, looks at a landscape of exposure into which populations can imagine themselves, right? You can think of your body as being vulnerable in that landscape. So this is a map made using photographic paper of hydrogen sulfide volcanically produced in New Zealand, and you can see you're able to cover a very large area with this method. So it's accessible to opportunities for covering a landscape. It's low cost, it's easy to use, and the results are visually compelling. So the areas with the darker test strips are the areas with higher H2S. So to some degree, it's more legible than a graph, and it's sensitive to these low levels of the communities might be chronically exposed to. So Lourdes went through how this is made, so I'm just going to skip over these slides in the interests of time. But basically, we cut up photographic paper, we put it in a light-safe container, and placed them out in the field. And so community members like the McMullins chose areas around their ranch to locate these film canisters, and they placed them systematically around the well that they thought was the source of hydrogen sulfide on their property. And they also took grab samples of air using buckets. Then they mailed everything back to us at Northeastern, to the darkroom. You can see this is really do-it-yourself. The idea is to tool that people can figure out how to make themselves, and to now come up with a way in which they can verify or to some degree certify the kind of knowledge that's produced using that method. And so here are our results on that ranch after 8 days and after 23 days. And what's really striking about this image is that you can see the control spot. So everything was tarnished. So there was a higher level of corrosive gas present across the area. And we saw the highest point at D4, which is the site of discharge, where the water that's produced during oil operations is supposed to be discharged cleanly into their irrigation system that then goes into the streams in their area. And because we use multiple methods in this study, we can see the results of their bucket echo that story. So they took a bucket sample at that moment, and they found a whopping 48 parts per million hydrogen sulfide in that single bucket sample. If you remember, the average threshold for a workplace ideally now is 1 part per million. So this is really a shockingly high level of hydrogen sulfide. So what difference does it make for a community to be able to think with these two ways of representing the hazard simultaneously? And I argue that it really gets to the heart of the way that H2S is currently framed as something that is a periodic and accidental release. And what we are showing much more is that it's actually chronic and long-term. So what we have in combining the bucket sample with the photopaper tool is a longitudinal view and a short-term view, both of which find high levels of H2S. And the fact that we find the highest level in the same place over 2 time periods shows that H2S must be chronically released in that site to results. So beyond providing this compelling visual data, they are literally data-rich test strips. So we can investigate, because they've been out in the world, what has landed on that test strip, what's reacted with the silver in the time that it's been out there. So this. These images we're moving towards here is actually kind of creating a data-rich result that's very similar to how electronic monitors actually work. So if you were to take apart a Jerome Meter, what you'll find is a gold film sensor in there that's working on the same principles of corrosion of that gold filter. It's just, so what we're doing with the photopaper tool is really raising up this method of detection to the surface rather than burying it within this black box. And arguably, every scientific device that's going to detect anything must have some kind of reactive medium that's able to be changed as an index somehow packaged within it. And so what I'm really interested in this process by is kind of bringing that to the surface rather than burying it. So back to this idea that these test strips show that the H2S releases are actually chronic and routine. So we see on these images that the H2S is spreading from the industrial site, so it's actually impinging on the private property's land. And we see this again in the other 3 public spaces we tested. I'm just showing results from 2 of them here. But we worked along public roadways through old oil fields in Elk Basin and Hamilton Dome, and found again that the hydrogen sulfide was traveling into those public spaces. And so this gives a way of representing to the public that that uses these streets that they may well be exposed, right? So it's a form of helping to build community advocacy and a sense of community exposure through reflecting data in this landscape way. And we found again in the other places that we tested that the H2S wasn't periodically appearing. It was appearing after 3 weeks, and it was appearing after weeks through a gradual darkening of the test strips, showing that this is not just being accidentally released at one time. So really helping to create a powerful argument against the way that it is presently, the logic behind its present regulation. And at the same time to build a sense of community, of exposure to ground advocacy. So if the hydrogen sulfide testing strips kind of condense time so you can look at H2S emissions over a period, I'm working on another project that's trying to create a real-time experience of environmental contamination using what we call the thermal fishing bob. It's again a very device, something that somebody can build in an hour with no previous electronics experience, using an Arduino, a thermistor which changes its conductivity based on temperature, and a light that changes, a three-color LED that will basically change the color of the light. And so what the thermal fishing bob does simply is connect a measurement of temperature to a change in the color of a light. And that means you can drop it into a source that you're interested in characterizing and move it through that source while taking a long exposure photograph and basically paint the surface with the data. So creating another kind of data-rich image that is interpretable as it getting warmer as you cross through. This here is an image of the discharge from the power plant along the Charles River in Kendall Square. And so we've been working on building these as kind of collective events. This is another test we did of thermal fishing bobs at RP on Earth Day, where we threw ice water into a pool and then organized people to try and fish to find that source, with this idea that we can create a set of devices for exploring our environments as a collective and bringing that idea back of collective witnessing into environmental science. So that we can kind of invert the lab again and bring the lab back out into the field using tools that people can make themselves, and so to some degree understand how they're functioning and can question the evidence as they are part of producing it. This is another event we had this fall working with an artist collective from Brooklyn, Maya Libram, where we floated thermal fishing bobs in children's pool floaties and towed them behind homemade canoes across the Mystic River to try and visualize thermal pollution from the Mystic power plant. You know, there's a lot of work to do to really refine these methods of kind of creating a real-time data performance or data experiment. You know, light pollution is really makes long exposure a challenge for visualizing these things. So if anybody with better experience at photography and more experience with performance art is interested in talking with me about further developing these ideas, I would love to discuss that. But just to wrap up, as ways of thinking about making invisible and collectively experienced environmental health threats more apparent, more manifest, I think we can re-emphasize the indexicality of scientific instruments and try and bring that index to the surface again, as well as bringing back witnessing and performance into environmental science. Thank you very much.